Swayam Prabha. Digital India. Educated India.
You mean the number of equations is more than number of variables, right? Yeah. So then how you can, so it is true for any general, I haven't yet considered anything, any restriction on the M and N. It is true in general. So it will come to when there are some particular cases will arise when M is too much, or number of number of equations are more compared to the number of variables. Yeah, so that will come. So that will be kind of the approximation of the solution. That will come later. In that case, I mean, B may not be in the column space all the time. It will be outside the column space. So for that, what kind of solution will be approximating with, that will come later. This will always hold when B belongs to the column space. For that also, you will have a column space which is narrow, maybe narrow, but it will have. We are considering B in the column space. Whenever B is in the column space, we will have a solution. And whenever we have a solution, this is true. So that is what we are considering. We are currently considering B is in the column space. So that means that we will have a solution of the system of linear equations. When B is outside the column space, what we will do, that we will see later. Okay, so that will come in the next topic. We will be considering that. But okay, so this is again the repetition of what we have seen. For a square matrix, especially for a square matrix, if n is the n columns of A are independent, n columns of A are independent, then what? If n columns of A are independent, then what will happen? We are considering now a square matrix M. So this column space of n columns are independent. So that will be a full column rank. That means this will be 0. So that total column space will be your Rm. So any vector you choose, that will be giving you a solution. When your column space is the full Rm, any vector you choose, any vector B you will choose, you will be getting a solution. So that will be your, is always solvable. So that's the first point. Okay, is it clear? And second point is what? Only one solution. Only one solution when? When this space is 0. Only one solution when this space is 0. Solvable when this space is 0. Right? Only one solution when this space is 0. Solvable when this space is 0. So only one solution means this space is 0. So this is this will be giving you the only one solution corresponding to the equation, system of equations. Okay, so now as you are saying that will be, so second part of fundamental theorem is more or less over, because we know now the fundamental subspaces are orthogonal, and also they are orthogonal complement, right? And we can also see that how the solutions are actually split into two components, and how they are mapping with the corresponding column space and the corresponding column space, right? So that we have seen. So that's the second part of your fundamental theorem. But we want to know a little bit more, because as he was saying that if the number of equations are more and B suppose is not belongs to the column space, then we don't have the solution. Then what we will do? So for that we need to understand. So that's called the approximations. We cannot find the exact solution, because in many applications you will see that your number of solutions are huge. That means that number of variables are less, only say 1 or 2 variables, right? So in that case, what will be your the column space? Column space will be very narrow, like it's just number of columns are say 2 or 3. So that will be a 2-dimensional or 3-dimensional space, whereas number of equations are say 100, right? Number of equations are 100. So Rm is 100-dimensional space, whereas your column space is just 2 or 3 dimension. So it is more likely when you will choose a B from the Rm, so it will not fall on this 2 or 3-dimensional column space. So, and if B is not falling in the column space, we will not have a solution, right? So what we will do, we will do projection. We call it we will do some kind of least square approximation, what we will see in machine learning very often, that how we'll approximate, find an approximation solution, which is the kind of the best approximation, right? So that we'll do in the, we need to understand a little bit of the projection operation. First, you have already seen the projection onto a line. So when you have a vector and a line, when we will have a vector and a line, how we see the projection of this B vector on this line. You know that how to compute the projection, right? So what to do, how we can, so basically, so the key is the orthogonality, what we have just studied just now. Two vectors are orthogonal. So you see that we want to find this is the projection vector. This is the projection vector along this line. So we want to project this B vector on this line. Now, what is the, if we want to project it, projection will be this vector will be perpendicular, orthogonal to this line. Right? Is it true? We are projecting B vector on this line. Or projecting this point B, so the projection will be so that this line is perpendicular to this A vector. So that means that we have to find this. We have to find this length, this vector P, right? So basically we can write P as x cap into A, P as x cap into A, because this is x cap is a scalar multiplication, scalar multiplier. So we are multiplying this A by scalar quantity, so that we are getting this length, right? And how we are getting this? So if we just write it as projection onto a line. So we have this, this is the origin, this is a B vector, and this is the line, say, this is the line A, this is another vector. So we want to find the projection of B onto this line A. So that means that we have to find the line which is orthogonal to this. So my projection vector P, which I want to find, is this is my P vector, right? So we have to see that this is orthogonal, it's perpendicular. So this we call this E vector. E is equal to what? B minus P. Is B minus P. Is B minus P. Now to find one thing we already know. So this P is along the same direction as A. So we can write P as x cap into A. X cap is a scalar quantity. X cap is a scalar quantity. So basically what we have this E is perpendicular to A. It's perpendicular to A. Okay. Or perpendicular to P, the same, the perpendicular to P. So what we do, so this implies what? This implies if we consider B minus P dot x cap A, x cap is not required, right? So only A will be okay, equal to 0. This perpendicular, right? Now P, we have already expressed P as B minus
x cap A dot A equal to 0. This implies x cap is what? A dot B divided by A dot B or B dot A, both will be equivalent, right? There you can take that. A dot A, right? So you can also write it in the using the matrix notation A transpose B by A transpose A, right? So this is one quantity x cap, scalar component, and your actual vector is A transpose B by A transpose A into A.
Right. Now we are also interested in the projection matrix. So if you write it as this projection vector P, if you write it as you can write it as A transpose B by A transpose A, right? This is just we are writing the scalar quantity first, vector quantity first, scalar quantity after. And now what you can do, you can also take this operation A transpose by A transpose A B. Now what is your A transpose? So suppose we are considering this B as m dimensional. All these vectors are in Rm. Your vector A, vector B, all these are in Rm. Then what is your A transpose? So A is a column vector of dimension m from Rm. A transpose is a row vector. Now if you multiply a column vector with a row vector, what you will get? No. You see the dimension. So what is the dimension of A? M cross 1. What is the dimension of A transpose? 1 cross M. Then what is A transpose? M cross M is a matrix. So this is a matrix of dimension. So this is a matrix of dimension M cross M. This is a matrix of dimension M cross M. You can say something more. So this matrix will always have rank 1. This matrix, when you are just multiplying a column vector with a row vector, so it will always have rank 1. So these are called rank 1 matrices. Okay, this will have some significance in singular value theorem, singular value decomposition. We will see later. But you just can you try? This is your homework. Please check that this matrix will have rank 1. Okay, and so this is this we can write. This involves only the A vector. You just see this involves only the A vector. So we write this capital P. Capital P is the projection matrix. So this is a matrix, and you multiply this with this B. This projection matrix you multiply with this B, and you will get your projection vector P. So this is P. So there are 3 important things we are computing. First is X cap. Second is P vector, right? And third is the capital P, the matrix, right? Okay. So we have computed this. So we have computed the P vector, we have computed the projection matrix. So some property you can just verify that if P is M by M matrix, and also there is this condition will always be true. if you just projection of projection is again the same. If you project twice, that is P2, if you multiply P by P, then again it's the same matrix. That is projection of projection remains the same. Okay. Another thing you can see, if you consider P, capital P, and multiply that with the B vector, so that will be giving you the projection along the direction A, that is. But if you consider I minus P, I is the dimension, say, the identity matrix in RM. Identity matrix, that is the of M by M dimension, right? So that will be giving you the projection along the orthogonal direction, perpendicular to A. Okay, so this is the second property you can prove, that I minus P is the projection matrix along a line perpendicular to A. One is along the A, another one is along the perpendicular to A. Okay. Now suppose I give you this example. Find the projection matrix P, capital P, along the line. So you just can, given a line, you can always find its projection matrix, right? By computing A transpose by A transpose A. It depends only, and then you given any vector B, you just multiply that and you will be getting the projection vector P. So this is very important to understand, that given the line direction along which you are going to project, you can always find the projection matrix capital P. Right? You do not need the B vector to find the projection. Right? First, you are given the direction, you can find the projection matrix. So can you try this one? So just compute the projection matrix capital P. Projection matrix capital P. What is the given? 1, 2, 2. So A vector is 1, 2, 2. This is the column vector I have written in this form, right? This is a column vector. And what is the projection matrix P? This is the A transpose by A transpose A. A transpose A will be 1, 4, 4, A 9, right? 1 by 9. And what is the matrix? So 1, 2, 2. No, I have to write it in this way. 1, 2, 2, 1, 2, 2. So 1, 2, 2, 2, 4, 4, 2, 4, 4. So this is your projection matrix, capital P. Now one thing you notice, that when you are making this matrix capital P, you just see that one row and the other rows are a multiplication of that particular row. So how many independent rows are there? Only one. So what is the rank of this matrix? 1. So that's the kind of intuition why this is called the rank 1 matrix. Okay? It's called the rank 1 matrix. You can note it down. It's called the rank 1 matrix. So now you are given, say, any vector B. B is 1, 1, 1. B is 1, 1, 1. B is 1, 1, 1. So then what is your P vector? So capital P into B. So that is your 1 by 9 into, so you just compute this 1, 1, 1. So you will get the projection vector P. Okay, so we have now computed the projection of a vector onto another vector or onto a line. But what is our goal? So our goal is to, like as I was starting with, so our vector B in this equation Ax is equal to B is not lying in that column space. We want to find the nearest solution, kind of approximate solution. So we have to project that vector B onto this column space. So that is our goal. We have to project that vector B onto that subspace, column space, so that corresponding to that projected vector will have a solution. Because B, unless it is in the column space, we cannot find a solution. So we need to find the projection. So for that, we need to understand projection on a subspace. So far we have found the projection on a line. So line, you can now, instead of line, you have to consider a subspace. It's nothing more. The formula, everything will be similar, right? The subspace will be generated by a set of vectors, right? So this will be generated by a set of vectors, and you have to find the nearest point from the B to this subspace. The same picture what you have drawn, you have to now consider this only for this subspace. So what is my P now? P will be a vector in the subspace. So P can be expressed as the linear combinations of the vectors. So one thing I'll just assume that the vectors A1, A2, An which generate this subspace are linearly independent. Okay, so that I'll assume for certain reason. But you can start with also linearly dependent vectors, but later you have to find this set of vectors which are linearly independent. Okay, so that's the kind of the optimum set of vectors we'll start with, right? Otherwise, there will be some will be redundant, and you will be stuck at some point if you are having some of the vectors are you will not be able to find the actual dimension of the subspace. So that's why we will start with the linearly independent set A1, A2, An, and we need to find the projection vector P. There it was only one line, that is the one-dimensional subspace. So we consider only x cap into A, but here we have, say, n-dimensional subspace, right? N-dimensional subspace. So we have to consider their linear combination x1 cap into A, x2 cap into A2, and xn cap into An. So that is our vector. So we have to find this x1 cap, x2 cap, xn cap, so that this P, point P, is the projection vector of this vector B. So in the previous one, we had to find only x cap. Now we have to find x1 cap, x2 cap, xn cap. So that's the only difference. Is it clear? So when we are projecting, so we have to find this x1 cap, x2 cap, xn cap. So the key is the same, right? The observation is this error vector will be perpendicular to the line. So the same way I have done, you have to just consider. The only thing difference is that here A is a matrix and x cap is a vector. It is a bold, is a vector, and this is a matrix. There it was a vector and a scalar. So that is the only difference. The rest all other treatment will remain same. And if you do that, like the way I have computed x cap, here also you will be able to find that. So here we have to consider what? So each of the vectors, right, will be perpendicular to this error vector. Each of the vectors, this A1 vector, A2 vector, An vector will be perpendicular to this vector B. The error vector, right? So that will be giving you this set. So should I write it down, or I think it is okay. So this is a very important set of equations. Now what is the dimension of A transpose A here? So what is the dimension of A, we said? So that these vectors A1, A2, An are coming from, say, m-dimensional space, so Rm. So this will be m cross m, right? This will be m cross m, A transpose. So we have taken the vectors A1, A2, Am from Rm. So you can also relate it with your column space, the column vectors. Column vectors were each were from Rm, right? Column vectors were from Rm. So what is the A transpose? A transpose will be n by m. Now A transpose is what? So A is your m by n, and no, A transpose, it will be n by n. It will be n by n, right? So A transpose will be n by m into A. So it is your n by m, n by n. As we were able to see in the, when we are projecting the vector along the line, we obtained this x cap equal to what we had got, A transpose A, A transpose B by A transpose A, right? So that was, but here also we are getting the same thing. We are getting this capital A. These are the metrics. Now one property. So that is the reason you can prove. That is the reason I chose the column vectors as linearly independent. If you apply that, the column vectors are linearly independent, you can prove this. A transpose A, this n by n matrix is invertible. If you take the column vectors of the matrix A are linearly independent, then you can prove that A transpose A is invertible. Now what will happen if it is invertible? This system has exactly one solution. This system has exactly one solution. So that will be, you will be getting this x cap vector uniquely, right? You will get the x cap vector uniquely. So you will get the unique solution of this normal. This system is called the normal equations. So these equations you have to use, I think, all over your study of machine learning, when you will be studying this least square equation, finding the projection. You always need to use this, right? So this system is kind of the heart of studying this projection. So given any set of say system of equations, say x is equal to b, if b is not lying in the column space, you multiply by A transpose on both sides and you solve that system. Provided your column vectors are independent, column vectors of A are independent, you can find the x cap. So x cap is giving you the projection vector, this projection vector P. So you find x cap, and this will be, and you can also write it in the matrix form the way I had written for the projection on the line. So these are few important properties. A transpose A is a symmetric matrix, n by n symmetric matrix, and A transpose A is invertible provided your column vectors A1, A2, AN are independent. And another nice property is E. E belongs to the left null space. E belongs, that is a significance why I required this. E is in the left null space. How can you prove that E is in the left null space? Yes, you can see from this equation, the first equation. So this is equal to 0. This is equal to 0 coming from this, right? This is equal to 0 means what? This is in the left null space of A transpose, right? Okay. Okay, so these are all the expression, but you can easily find similar to those projection on the line. Projection on the line. I think this example you can try yourself, right? I think I can, because we have 5 minutes. How many minutes I have? So okay, so this we can compute similarly. Like you have to find the A transpose. You just need to compute all those matrix multiplication and then find the projection vector on a subspace. I just leave this for your homework, or maybe you will be come to this example in your tutorial, right? I'll just set this in the tutorial. So now this is the this application of whatever you have just seen. So from this part onwards, it is simpler because if you have already understood the projection on the line and projection on the subspace, the least square approximation is simpler. So the problem is, like as we started with, we have too many equations, but number of variables are very less. So the column space column space spanned by the columns are actually narrow, very narrow. Say we have 100 equations, so Rm is R100 and the column space is 3-dimensional. So it's negligible, it's very small. And when you choose the right hand side B vector in this equation Ax is equal to B, it is unlikely that it will always fall in the column space. It will be near, but it is not in the column space, then you will not have any solution of this system Ax is equal to B. So Ax is equal to B is not solvable most of the time. And you will come with this kind of equations often. Okay? So you will have too many equations and very few variables. So what you need to do? You need to, so when Ax is equal to B is not solvable, you just multiply with this A transpose on both sides, get a system of this normal equations and solve them. So your m is 100, but n will be say 3, right? So you'll be getting a 3 by 3 matrix, 3 equations with 3 variables. You can always solve it if it is invertible. So you find the solution, right? You find the solution and find the approximation x cap, which will be giving you the projection, the nearest solution. Now there are a few properties which you can try to prove. Basically the geometry is like that. When you are trying to find the projection, you are choosing this, the error vector E is perpendicular to the subspace, the column space, and you are projecting that. So basically, so that will be giving you, so you can see that the best possible projection is when this is perpendicular to the subspace, right? That then you will be getting the best possible projection. So that's the one way of explaining that why we should do the projection. There are many other ways. There are 3 different ways actually. One is the using geometry, one is using the algebraic way, one is using the calculus way, but you will be getting always leading to this system of normal equations, which is A transpose A into x cap is equal to A transpose B. So the algebraic way is that, so a little bit that is why we chose this E vector belongs to this left null space. So we can, when this B vector is outside your column space, when this B vector is outside the column space, you can split this into this vector and this vector. So one will be your P, right? So that is the projection vector P. So here we are projecting B. Corresponding to this, we will have the solution because we know that this x cap. Now we solve this equation to get the, so this P will be giving you the projection, right? So we have the projection here and the corresponding error here. Error we ignore, right? So so you can check algebraically. So this if you split into this is the algebraic way. So you just split the vector B into P plus E. P is the projection vector and E is the error vector. And then you show that this, we try to minimize this capital E over here. So this is minimized when P is the Ax cap. Why is that? This is minimized because when this expression in E is minimum, this Ax is equal to P if it is 0. Because, right, E you can express this Ax minus P plus square plus is 2 square addition sum of 2 square terms, and this E will be minimum when this first term is 0. Is that okay? So, but I think if you understood the geometric way that this error vector is normal to the subspace, that is also giving you the same. But it is another way of explaining the same thing, that if you express the B vector as the sum of 2 vectors, one will be in the column space and one will be in the left null space, that is the error vector. So you consider only that projected part in the column space and solve corresponding to that. So that will be giving you the the best result, the best approximation of the your given system of linear equations. Okay, so this is one application, right? So you understood you have understood now the projection on the subspace and the least square approximation. So that will be actually applied in several data sets. Like you are given, say, a set of points in 2 dimension. You want to fit a line which will be giving you the best line, right? So you have to, now when you have say 100 points in the plane, and if you want to approximate with a line, the line will have how many parameters? 2 parameters. So either you have to choose the points very carefully so that it is lying on the line. So then in that case you will have a solution. Or otherwise, most of the time when the points are coming naturally, so they will not fall on the same line, right? So in that case, your system Ax is equal to b will not have a solution. So it will have error. So the line, when you are choosing a so these are given points, and you are choosing a line, so you have to minimize these errors, right? Minimize this distance from the point to the line. Okay, so this you have to minimize. That is your least square approximation you have to apply, so that this will come to the same application of the least square approximation. So we will be getting the matrix A, which will have, say, Tm. So if the number of points are, say, 100, here you will have 100 by 2 dimension, right? So this will not have a solution. So you have to find we have to multiply with A transpose on both sides, then find the solution, and that will be giving you the approximate solution, or the least square approximation of the solution. Okay, so given set of points, now you can compute using this formula that what will be the corresponding so this x cap will be giving you the best C and D. So if you solve this system, you will be getting best C and D, and that you plug in your line, and that line will be giving you the best line fit of the given set of points. Okay. Similarly for the parabola. If you want to approximate with a parabola, so then you will have 3 parameters, right? Here also you will have, say, 100 by 3 dimension of the matrix. Most of the time it will not have the solution, and you compute it with the best x cap using this formula, using this system of normal equations, and that will be giving you the best C, D, and D, which will be giving you the best parabola. A few more slides. Okay. So what we have seen in the formula for projection on a subspace and on a line, these A vectors, right? So these column vectors. So it is little bit computationally expensive, I would say, because A vector, I think if you do the computation, it will be a little bit more expensive when you want to compute the projection, if you are having this A vector as general column vectors. But instead, if we have some kind of property, nice property on those A vectors, which are these vectors are orthogonal or orthonormal, so it is then very easy to compute this projection. So basically the idea is, in general, given the matrix A, we transform this to the columns of this vector to orthogonal or orthonormal set of vectors. Okay, and then you do this computation, because then the computation is just very natural. The projection, you know that if you are given this 2 vectors which are not orthogonal, okay, then if you are given some vector A, if you want to project, you have to do a lot of work. But if you are having this kind of very nice system like this orthogonal or orthonormal system, right? Orthonormal system, the x-axis, y-axis, z-axis. So then it is very easy to compute the projection along the normal direction. So that is why the motivation is to first convert your matrix capital A into some kind of orthonormal matrix or orthogonal matrix by doing some kind of transformation of those normal vectors into a set of the column vectors into a set of normal vectors, and then you do the computation for your projection vector or projection matrix. So a set of vectors will be called orthogonal if any two vectors are orthogonal or perpendicular. Okay, and orthonormal when their unit or the length is also the unit vector, the unit, the one. So that is little bit more than orthogonal vector. So the length will be also of length 1. So we would like to satisfy this these properties in our column vectors. We would like to satisfy these properties in our column vectors, and that can be done using some method. It's called the Gram-Schmidt orthogonalization or orthonormalization method. So, so if you can convert your matrix A to this matrix Q, right? If you convert or if you transform your matrix A to matrix Q, where all the vectors are orthonormal, then this matrix will be called orthogonal matrix, matrix Q. And you will have this nice property that Q transpose Q will be the identity matrix. Now you see your formula, what you have given for the projection vector. So there it was like A transpose A. Now if you apply this Q transpose Q, so this will be all eliminated, right? So your formula will be simpler, right? So that is the idea of considering the Gram-Schmidt orthonormalization method to convert your matrix A to a orthogonal matrix, and then you compute the projection vector. So you will see that all these formulas will be reduced. So this is your, you replace the previous formula, whatever we have obtained for X cap, for P, and for capital P, the projection matrix, and you will be getting these simpler formulas. Okay, you need to write it down properly so that you understand. What you can see from the projection vector capital P, the second formula, what you can see, so this is the component of B along Q1. And then, so you know that how you write the vector in this vector algebra, what you have studied, some vector V is equal to 1 into I cap, 2 into J cap, 3 into K cap. The similar formula for n dimension, right? And this will be the n by n projection. So there will be nothing in the denominator. Denominator will be in, right? Denominator will be 1. Denominator will be 1. So there will be just Q transpose. Now one nice property you can check, if Q is a square matrix, that is your M and N both are equal, then P is equal to B. Why is that? So we have discussed already, then B will be lying in the column space, then P is same as the B. If you have a square matrix, then this projection, if you have a square matrix, so it's the B vector is already in your column space, right? So if B is in the column space, then the projection is the same. So B is equal to B. That's one nice observation you can just check. So now finally the Gram-Schmidt orthonormalization method. So you start with, like we started with the set of linearly independent vectors, right? We started with set of linearly independent vectors, and we want to transform them to the set of orthonormal vectors. Orthonormal vectors. Just see the idea of how you do it geometrically. So first you are given these vectors A, B, and C, which are linearly independent. Right? And we want to convert them to first two set of orthogonal vectors, and then you just divide by their length to get the set of orthonormal vectors, right? So there are two steps. First you convert to orthogonal vectors and then set of orthonormal vectors. Now, if you have to take the vectors one by one. First take the vector A, small a. So this is forming a orthogonal set of vectors. For the one vector it is okay, right? For one vector it is satisfying the definition. We do not need to worry. When you take the second vector, you see this picture. When you set the second vector B, right? Or you go back to your previous, I think this picture is also okay. You take this vector. So it will have two components. So one component will be this component and this component, right? So this component is what? The projection of B on this A. So this error vector will be orthogonal to A. So for the second vector, we are choosing, this is the error term, what we have considered there. So that is the orthogonal. So now we consider, instead of small b, we will be considering capital B, which is orthogonal to, capital B is this one, which is orthogonal to A. So not the projection vector, but the perpendicular to the projection vector, right? And you go on in this way. So first you take one vector, the second vector, that will be orthogonal. You take another vector, second vector, you take the error term in that projection, whatever we have considered. So that will be orthogonal to A. So that will be, these two are orthogonal now. Now we consider the projection on this subspace spanned by capital A and capital B, right? We consider projection, consider the error vector to this. So when we are considering the third vector, so first we consider the this A and B, and this is the span, and you project the C vector on this subspace generated by A and B, whereas this error term will be your C vector. Yes? So this is the span. First we have considered A and B. So this is the span. This plane, one plane will be generated by A and B. Now when you consider the small c, you consider the projection of small c on this plane. So then you consider the error corresponding to that E. So that is, error term is perpendicular to the span generated by A and B. So that error term we will be considering here. We have considered similar expression before. So that way you just go on till you finish all your set of independent vectors. So that will be giving you the set of orthogonal vectors, and then you just divide in the third step, in the second step, in the so you can see that you just divide by the length of those vectors to get the Q1, Q2, Qn. Okay, so this will be giving you the set of orthonormal vectors by which you can now compute the projection operation, projection vector, projection matrix, and you compute the system of solve the system of normal equations to get the best approximate solution, right? And you solve by problem like the line fitting or the parabola fitting to a given set of data. Okay, this example you can just, I can put it in the tutorial, and you can just try to compute it in the tutorial lecture. Thank you very much for your attention. Yeah, I hope you have understood a little bit. Yeah. Okay, thank you. So in the next class, I'll move on to the Thursday's class. We'll be looking at, so this actually covers the second part of the fundamental theorem of linear algebra, including some more thing how we can approximate the solution, right, using the projection operation. The next class we'll be going to that the singular value decomposition, which is kind of the heart you have to understand for many problems in machine learning. Okay, so but these all have some nice applications in the machine learning. Okay, good.